Okay, we're going to work to derive some more vector identities involving, of course, the del operator as it applies to the position vector. And here's our definition of the position vector, either as we're operating on a position vector or as we're operating on the magnitude of the position vector. And the magnitude of the position vector is a function of x, y, and z. It's just the square root of this quantity, x squared plus y squared plus z squared. Now, in previous videos, we've shown that the divergence of a position vector is 3, the curl is 0, and we've also shown that if we take the gradient of the magnitude of any position vector, that is equal to the unit position vector. And we've also shown that the Laplacian of the gradient of any position vector is equal to 2 divided by the magnitude of that particular position vector. In previous videos, we've shown this relationship. This applies to any vector, where here we're taking the gradient of some scalar quantity that is a function of u, where u itself is a function of the variables x, y, and z. Actually, we should write it like this. U is some function of these variables, x, y, and z. We've shown this to be true in the previous video, and then we used this relationship to prove this identity, that when you take the gradient of the scalar of any position vector raised to the n power, it's equal to this expression. And now, in this video, we're going to show that the Laplacian of the magnitude of any position vector raised to the power n is equal to this expression. So we're going to make use now of all this background information. In addition, we have 6 videos where we prove various types of vector identity operations with the del operator. We're going to make use of those too as we proceed through these vector identity operations. Okay, let's see how we handle this one. Here then, this, we know by definition that this is the same thing as this. Del dot that's just the definition of the Laplace. And we know that this quantity right here is this. So this is equal to del, taking the dot product with this quantity, n times r to the n minus 2 times the position vector. So here we have a situation where we're taking the divergence of a scalar times a vector. And I think it was example 3 in our vector identity series where we dealt with this kind of a situation. And if you watch those previous videos, you know that how we handled it, we get this kind of expression. This is equal to the gradient of the scalar and taking the dot product of that with the vector. In this case, it's just vector r, the position vector, plus this gradient times the divergence of the vector. And in this case, it's the position vector, and the divergence is 3. So this is equal to 3. And this is our expression. Okay, now to continue, we have to determine what is this. So here we have the gradient of n times r and n minus 2. And that is where this expression comes in. So this is equal to the derivative of this expression with respect to r of n times r to the n minus 2. In this case, it's Lr. So again, that's where we make use of this relationship. And what is del r? You know what that is? That is just the unit position vector. So this is this. And the unit position vector, that is just the position vector divided by its magnitude. So we have this. Now we can take the derivative here. That is equal to n times n minus 2 times r to the n minus 3 times the position vector r divided by r. Or we can just write this as r to the n minus 4 and get rid of this. This is r to the n minus 4 times the position vector. So this is this, and what are we supposed to do with that? Let's take the dot product of this with the position vector. So you might take the dot product of this with the position vector. And r dot r, that's just r squared. So with this expression right here, we're going to have this. This is equal to n times n minus 2. Here we have r to the n minus 4 times r squared. That's going to be r to the n minus 2. Plus we have this expression, plus 3n times r to the n minus 2. Again, that is what we're saying that this is equal to. So let's see. Here we have minus 2n plus 3n. That's plus n. So looks like what we're going to end up with is this. It's going to equal n times n plus 1 to r to the n minus 2 power. And that's what we were asked to show. That's our identity. So there it is. As you can see, it's not a very laborious process. In fact, it's pretty much a very efficient process. But again, there's a lot of background now that we're incorporating into these problems. So if you haven't seen those earlier videos, I think you'll find them worthwhile to go through them, because we're going to keep incorporating this background information as we proceed through more topics in vector analysis. And we're going to try look at some more vector identities involving either the position vector or the magnitude of the position vector. So come back and join us for those videos, and we'll try and solve some more problems.